Shock advised. Stand clear. Push shock button.
Attack priority 1.
Hi. So I severely underestimated how long this video was going to take to create, so I'm splitting it up into a couple different parts. Each part is going to have the same intro, which is just kind of a overlapping review of smooth muscle contraction and relaxation, and then I'll actually get into the different pathways of such. So this video is for contraction pathways, more specifically the IP3 and DAG pathway and the ROK pathway. So please enjoy the video. Thanks for watching. This out here, like an action potential or receptor stimulation. And what that is going to cause is it's going to cause some calcium to enter from the extracellular membrane, and it's going to cause calcium to leave the sarcoplasmic reticulum. So you'll have this calcium in here. Oh boy, calcium really wants a friend. It's going to hang out with this protein out here called calmodulin. Now, once calcium and calmodulin are combined, well, the myosin light chain kinase enzyme, or MLCK, wants to hang out with them. So it's going to go into its active form. Now, when myosin light chain kinase is in its active form, what it is going to do is it's going to take an ADP or an ATP, and it is going to break off a phosphate, creating ADP plus P. Now, where does that phosphate go? Well, it goes on the myosin heads here so that they can interact with this actin up here, causing a muscle contraction. And the muscle contraction is going to go this way. If there was one over here, it would go this way. So this is kind of everything that we talked about so far. Now, how does it get inactivated? Well, boy, howdy, I am so glad that you asked, because let's see here. I want my pen, and here we go. So remember, calcium comes down here. It's going to hang out with this calmodulin here. Calcium's entering, calcium's leaving the sarcoplasmic reticulum. It wants to hang out with calmodulin. Once calmodulin and calcium are hanging out with each other, it's going to cause MLCK, or myosin light chain kinase, to combine with that calmodulin. And then this active MLCK is going to take an ATP. It's going to split it into an ADP plus P. These phosphate molecules are going to attach to those myosin heads, which allows it to interact with this actin over here, causing a contraction. Now, when your body is tired of contracting, basically everything that happened is just going to go in the reverse. So we'll use red. So ATP is going to actively transport calcium back into the sarcoplasmic reticulum. ATP is going to actively transport calcium through some calcium channels in the cell membrane. You're going to have some sodium entering because your cell likes to maintain that charge balance. And then once this MLCK is inactivated, well, it's going to cause MLCP, which is myosin light chain phosphatase. Now, if you know anything about enzyme, basically tells you what it is. So ASE is going to be an enzyme. Phosphatase, it's going to break down phosphate. Now, where is it going to break down phosphate from? Well, boy, I'm so glad that you asked. Myosin light chain phosphatase is going to come up to all these phosphates. It's going to delete them. And then your cell is going to relax. Does that make sense? Okay. If it didn't, well, I'm sorry, because what we're about to get into next is quite dense. All right. I just wanted to make sure that I was recording because I couldn't see my OBS, and I didn't want to have to, re-record all of that. Okay, so we're getting into the IP3 and DAG pathways now. It is one way that your smooth muscle cells will contract. Okay, so let me just draw some labels here. I'm going to fast forward the video. Okay, so what do we got going on here? So this is going to be the IP3 and DAG pathway. We'll get into how this all works. This is just one way that your smooth muscle will contract. So let's see here. What do we got up here? Well, this is going to be a receptor, and just to make things easy, this is going to be an alpha 1 receptor. And when an alpha 1 receptor antagonist say, this is critical care, so we're going to say, oh, norepinephrine. So norepinephrine is going to combine with this alpha 1 receptor. Now, what happens? Well, there's going to be a couple of things that happen. Well, this alpha 1 receptor is going to come over here. It's going to go all up and down these tubes, and it's going to get to this G protein coupled receptor complex, more specifically this GQ protein. Now, when this GQ protein over here receives a stimulus, it is going to move over to this protein over here. This protein is called phospholipase C. And what phospholipase C is going to do, well, it's an enzyme. It's got the name ACE. There's some lipid terminology in there. It's going to break down a lipid. More specifically, it is going to break down, now let's see if I can remember how to say this, phosphatidylinositol 4,5-biphosphate. Now, phosphatidylinositol 4,5-biphosphate is going to break down into two things. And for the sake of everything and everyone's sanity in my English speaking skills, we are going to call this PIP2. Now, what PLC or phospholipase, it breaks down PIP2. It's going to break it down into two things. The first thing it's going to break it down into is ionositol triphosphate, or IP3. So we're going to say IP3 because I can't use words correctly. And it is going to break it down into diacylglycerol, or DAG, D-A-G. Now, what IP3 is going to do is it's going to come down here, and it is going to stimulate the ever-loving crap out of these calcium channels. Now, what the stimulation of these calcium channels in the sarcoplasmic reticulum is going to do is it's going to cause a lot of calcium to exit. So we'll see. Boom. We're going to have a lot of calcium out here. CO2 plus, CO2 plus, Ca2 plus. And what that excessive amount of calcium is going to do is it's going to be able to form a lot of these activated calmodulin complexes. So calcium is going to bind to these calmodulin complexes. Now, there's a lot of these calciums out here, so there's going to be a lot of calmodulin complexes that can be made. And what does this do? Well, it takes our myosin light chain kinase inactive form, and it combines, and it's going to become an active myosin light chain kinase enzyme. Now remember, what does this myosin light chain kinase enzyme do? Well, I am sure glad you asked. It's going to take some ATP. It's going to break it down into ADP plus P, and this phosphate over here, it's going to bind to these myosin heads. So let's draw some arrows here. So we got ADP plus P binding with that phosphate. And what is this going to do? Well, I am so glad that you asked. It's going to allow the muscle to actually contract. So we got some phosphate here. We got some phosphate here. Bam! It's going to contract. That is supposed to be an arrow. And if there was one over here, then it would contract in that way. This is how your smooth muscles contract, but this is the IP3 and DAG pathway. Now, I'm glad you mentioned that I forgot something. Well, what about this diacylglycerol or DAG molecule over here? What is this going to do? Boy, I am so glad that you asked. Well, it is going to come over here, and it is going to activate protein kinase C. So this is the inactive protein kinase C, and what DAG does is it comes down here, and it's like, hey, get off your ass and do your job. So it's going to become the active protein kinase C. Now, what does protein kinase C do? Well, it's going to come down here, and it's going to come down here to CPI-17. This is a protein. Can you see that? CPI-17 is a protein, and what CPI-17 is going to do is it's going to attach a phosphate to our myosin light chain phosphatase. Now, when it attaches that phosphate or P, to our myosin light chain phosphatase, what does it do? Well, it turns it off. So as you might remember, myosin light chain phosphatase, it breaks off our phosphates from all of our myosin complexes here. And when it gets a phosphate added to it, well, it gets turned off, so it can't do that. This is the IP3 and DAG pathway for smooth muscle contraction. So we have like norepinephrine. It's going to stimulate this alpha receptor up here. It is going to go all the way through our receptor. It's going to activate this G protein coupled receptor complex. It's going to activate this GQ protein. This GQ protein is going to come over here to our phospholipase C protein, and it is going to break down phosphatide PIP2. It's gonna break down PIP2 into IP3. IP3 is going to stimulate these calcium channels, which is going to cause more calcium to be released, which is going to cause more calmodulin calcium complexes to be created, which is going to be able to activate more of our myosin light chain kinase enzymes, which is going to be able to take more ATP, break it down, and into ADP plus P, and those free phosphates are going to attached to our myosin heads over here. And what that is going to do is it's going to power the actin myosin complexes, causing a contraction. And at the same time, our PIP2 breaks down into diacylglycerol, or DAG, which activates protein kinase C over here, which is going to phosphorylize CPI-17, which is that protein we talked about. And the CPI-17 is going to come down here. It's going to attach a phosphate to myosin light chain phosphatase, and it's going to turn it off, preventing this contraction from being broken down. Does that make sense? Well, I certainly hope so. Let's see in the brain fart. All right, so what have we talked about so far? So we talked about smooth muscle contraction, relaxation. We talked about the IP3 and DAG pathways. Now we're going to talk about the ROK pathway. So let's go. Okay. Now this looks like a lot of nonsense here going on, but we will break it down and we will make it easy. I promise. Well, as easy as I can anyway. Okay, so let's look over here. So we have like something like norepinephrine. It's going to stimulate this receptor over here. It's going to go all the way through, and then we have this G protein complex. But unlike over here with the GQ protein, this is going to stimulate the G12 and 13 proteins. Now, once this G12 and 13 protein is stimulated, it is going to pick up a GTP. Now, once it picks up a GTP, it's going to go over to this enzyme called ROGEF. Now, what ROGEF actually stands for is Rho guanine nucleotide exchange factor. Now, once this enzyme becomes active, it is going to cause this over here. And what this over here is RAS homolog family member A, or just Rho A. And this is Rho A GDP because it has a GDP attached to it. So we got Rho A over here with a GDP attached to it. Now, once this ROGEF becomes active, it is going to cause this Rho A GDP to pick up a GTP. Now, over here, we have Rho A GTP. So, Rho A GTP. Now, this Rho A GTP is going to come down here, and then this is our Rho kinase. Rho kinase, or ROK. Now, these two are going to combine into the active Rho kinase. So this is the inactive form. This is the active form. So this is the active Rho kinase. And what this is going to do is it's going to come down here and it's going to phosphorylate our myosin light chain phosphatase. So remember, MLCP. More specifically, it's going to phosphorylate the MYPT1 subunit of the MLCP myosin light chain phosphatase enzyme. Now, when that happens, well, guess what? It can't break down the phosphates that we have on our myosin heads. So it's going to this smooth muscle is going to stay contracted. Now, do keep in mind that because this myosin light chain phosphatase is unable to break down these phosphates on these myosin heads, it is just going to cause the muscle to stay contracted, and your smooth muscle can stay contracted without using a lot of ATP, unlike skeletal muscle. And this is why, because there's nothing to break that down. Now, let's draw all this part out on the next slide. Okay. So we have a stimulus like norepinephrine or something. It's going to go through all of these tubes, and it's going to reach the G12-13 subunit. Now, when this message from this norepinephrine reaches this protein over here, we're going to pick up a GTP. So we got a GTP. Bam. Now, this protein is going to move over here to our ROGEF enzyme. ROGEF. Remember, this is the Rho-guanine nucleotide exchange factor enzyme. And then over here, we have RHO-A with a GDP. And this ROGEF enzyme is going to cause that RHO-A GDP enzyme to become RHO-A GTP. Now, once this becomes RHO-A GTP, it's going to combine with our Rho kinase or our ROK enzyme. This is the inactive. And then once they combine, it's going to become the ROK active enzyme. And it is going to come down here, and it's going to phosphorylate the MYPT1 subunit of the myosin light chain phosphatase enzyme. Myosin light chain phosphatase. And what that's going to do is, remember, you have all these phosphates here, which are allowing our myosin heads to keep the muscle contracted. Now, if this enzyme becomes inactive through, something like phosphorylation of the MYPT1 subunit, well, it can't really come up here and break those binds, can it? Nope. So that is the ROK pathway. Hi. So that was the IP3, DAG, and ROK pathways for smooth muscle contraction. The next video, we're going to get to the actual relaxation through the different pathways there. And then the last video is probably just going to be me compiling the 2 videos that I made together. Thank you again for watching. If you learned something, please like and subscribe. That really helps me be motivated to make more content to the 3 people that are actually viewing my videos. I hope one of them is not my mom. Anyway, thanks for watching. Happy studies.